25 trillion miles. That is the distance to the nearest star beyond our own, and our fastest spacecraft would take 70,000 years to get there. But a small group of physicists just published equations that warp space itself, a private lab in New York running simulations no one thought were possible, and a paper from 2024 that finally solved the problem Einstein left behind. We're going to walk through a bubble of bent space-time, a wormhole held open by impossible matter, and a signal astronomers want to hunt across the galaxy. If this is the kind of mission briefing you want more of, hit subscribe and stay with me. Strap in, we begin. Pull up the navigation console. The target is Proxima Centauri, a small red star sitting closer to us than any other stellar neighbour. On the star chart it looks like a short hop. The real number is 25 trillion miles. Write that figure out in your head. 25 followed by 12 zeros. That is the gap between our solar system and the nearest star outside it. Light itself, the fastest thing in the known universe, needs 4 years and 3 months to cross that distance. A radio message sent from Earth would not reach the planet orbiting Proxima until a child born today learned to read. Now bring up the fuel calculations. Every rocket humanity has ever built burns chemical propellant. The Saturn V that carried astronauts to the moon burned 3,000 tons of kerosene and liquid oxygen in its first stage alone. That monster of an engine moved a small capsule 250,000 miles. Proxima Centauri is 100 million times farther. Scale the math up and the numbers go insane. To reach the nearest star in a human lifetime using chemical rockets, a spacecraft would need more fuel than exists on Earth. More fuel than exists in the entire solar system, if you count every molecule of hydrocarbon on every moon and asteroid. The tyranny of the rocket equation says every gallon of propellant you add also needs fuel to carry it, and that fuel needs fuel to carry it, and the mass stacks up into a wall that no chemical engine can climb. Engineers have known this since the 1950s, which is why every interstellar mission ever sketched on paper has tried to sidestep chemistry entirely. Nuclear pulse propulsion, fusion rockets, antimatter drives, solar sails pushed by ground-based lasers. Each design claws a little closer to workable speeds. None of them crack the real ceiling. The real ceiling is the speed of light itself, roughly 670 million miles per hour. At that speed, Proxima is still more than 4 years away. At 1/10 of that speed, it becomes a 42-year voyage, and nothing humanity has ever launched comes close to 1/10 the speed of light. Our fastest spacecraft crawls by comparison. Look at the mission profile differently. If you wanted to visit 1,000 stars within our galaxy, and you had a ship that could cruise at a steady 1% of light speed, your grandchildren's grandchildren would still be travelling when the mission brief expired. The Milky Way is 100,000 light-years across. Our galactic neighbourhood alone contains hundreds of stars within 20 light-years of Earth, and every single one of them is, in practical terms, unreachable. This is the problem that every interstellar mission planner starts with, not engineering in the conventional sense, a blunt confrontation with the size of space. The numbers are so large they stop meaning anything to human intuition. So cosmologists reach for comparisons. If the solar system were shrunk to the size of a quarter, the nearest star would still be 300 miles away on the same scale. There is only one way out of this trap. You either build a ship that can travel for 10,000 years without failing, and fill it with generations of humans who never see Earth or the destination, or you find a way to break the speed of light itself. The second option was supposed to be impossible. A theoretical physicist in 1994 said otherwise. Swing the telescope outward. There are 2 spacecraft currently leaving the solar system, and both of them are humanity's fastest moving machines ever built. Voyager 1 launched in 1977 and crossed into interstellar space in 2012. Voyager 2 followed in 2018. They are the only objects we have ever sent beyond the edge of the heliosphere. Check their velocity on the tracking screen. Voyager 1 is moving at approximately 38,000 miles per hour relative to the solar system. That sounds fast. It is fast by every human standard. A commercial jet cruises at 600 miles per hour. A rifle bullet leaves the barrel at around 2,000 miles per hour. Voyager is moving 19 times faster than a bullet. Now plug that speed into the interstellar equation and watch the answer break your patience. At 38,000 miles per hour, the distance to Proxima Centauri takes roughly 70,000 years to cross. 70,000 years. The first cave paintings in Europe are 40,000 years old. Agriculture was invented 12,000 years ago. Writing is 5,000 years old. The entire recorded history of our species would fit inside 1/4 of a Voyager trip to the nearest star. And Proxima is the nearest star. If you wanted to visit Sirius, the brightest star in our night sky, the trip would take 150,000 years. Betelgeuse, the red giant in the shoulder of Orion, sits so far away that a Voyager-class probe would not arrive before our species likely went extinct, reformed, and went extinct again. The engineers who designed Voyager understood this. The craft was never meant to reach another star. Its gold record, the famous disk of human sounds and images bolted to the side of the probe, was built to last 1 billion years in the vacuum of space, because that is roughly how long the Voyagers will need to drift before they come anywhere near another stellar system. Voyager 1 is currently heading in the general direction of a star called Gliese 445, and it will make its closest approach in approximately 40,000 years, at which point it will still be 1.5 light years away. A light year is 6 trillion miles. 1.5 light years is not close. It is the distance at which the Voyager probe, after 400 centuries of flight, will wave at Gliese 445 from a vast emptiness and continue drifting. There is a newer record holder on the books. The Parker Solar Probe, launched in 2018, recently clocked speeds above 430,000 miles per hour as it slingshotted around our home star. That is more than 10 times faster than Voyager. Reset the calculation with Parker's peak velocity, and Proxima becomes a 7,000-year voyage instead of 70,000. Better. Still useless. Because the problem is not incremental speed. You cannot inch your way to the stars by building slightly faster chemical rockets. Every factor of 10 improvement in velocity only shaves 1 zero off an already unreachable timeline. You would need a factor of 10,000 to make interstellar travel practical, and the rocket equation refuses to deliver that kind of leap. Which is why mission planners started asking a deeper question. What if the ship does not need to move fast at all? What if space itself could do the work? And what if Einstein's own equations already permitted exactly that kind of trick? Open Einstein's notebook. The year is 1905, and a 26-year-old patent clerk in Bern, Switzerland, has just written a paper that changes how humans understand motion. The paper is called On the Electrodynamics of Moving Bodies. It contains a result so strange that most physicists of the era refused to believe it for years. The result is this. The speed of light in a vacuum is the same for every observer, no matter how fast they themselves are moving. A spaceship racing toward a beam of light at half the speed of light does not measure the beam coming at them at 1.5 times light speed. The beam still arrives at exactly light speed. Always. For everyone. Forever. That single fact breaks everything. If every observer sees light moving at the same speed, then time and space themselves must stretch and squash to keep the math consistent. Moving clocks tick slower, moving rulers shrink. The faster you go, the more dramatic the effect. Push the equations to their conclusion and a wall appears. As a spacecraft accelerates toward light speed, its mass increases. The closer it gets to that final velocity, the more energy the engines need to gain the next mile per hour. At 99% of light speed, the ship's apparent mass has grown by a factor of 7. At 99.9% by a factor of 22. To actually reach light speed, the ship would need infinite mass, and accelerating infinite mass requires infinite energy. Infinite energy does not exist, not in the universe we live in, which means the light barrier is not a technological problem. It is a geometric feature of space-time itself, built into the fabric of reality the same way the number 3 is built into the concept of a triangle. There is a hidden detail here, though, that most people miss. Einstein's rule says matter cannot be accelerated to the speed of light. It does not say that nothing in the universe can exceed light speed. The distinction turns out to matter enormously. The rule applies to signals, particles, and ordinary objects moving through space. If you are a rocket, a photon, an electron, a bullet, a sound wave, a thought, an information packet, a coffee mug, anything with a location, the ceiling holds. You cannot outrun a light beam. Space itself was never part of the contract. And here is where the mission brief gets interesting. Cosmologists already know that the universe is expanding and the expansion is accelerating. Distant galaxies are moving away from us so quickly that at a certain distance their apparent velocity exceeds the speed of light. These galaxies are not breaking Einstein's rule. They are not moving through space faster than light. The space between us and them is stretching. The galaxies are riding that stretch, like passengers on a conveyor belt that keeps getting longer underneath them. This loophole has existed since the first moments after the Big Bang. Inflation, the brief but violent expansion of the early universe, stretched space at speeds trillions of times faster than light. No law of physics was broken, because no object was moving through space. Space was moving. Mission planners stared at that loophole for decades, wondering if there was a way to exploit it on a smaller scale, wondering if a spacecraft could stay still inside a pocket of space while the pocket itself went somewhere. The idea sounded absurd. Until a young Mexican physicist sat down with Einstein's field equations and proved the math worked. Pull up a cosmology textbook. Turn to the section on the expanding universe. You will find a map showing galaxies scattered across the cosmic web, and you will find a number called the Hubble constant. That number describes how fast distant galaxies are receding from us. The farther away a galaxy sits, the faster it appears to move. Run the math to its extreme. Beyond a certain distance, roughly 14 billion light-years from Earth, galaxies are receding faster than light itself. Astronomers have a name for this region, the cosmological horizon. Any galaxy beyond it will never be reachable by any signal we send, because the space between here and there is stretching faster than any light beam can cross. This is not a theory waiting for proof. It is confirmed observation. The James Webb Space Telescope regularly photographs galaxies at distances that place them in this regime. Their light took 13 billion years to reach us, and during that time the universe kept expanding, so the galaxies themselves are now much farther away than the original light path suggests. Some of them have already crossed the horizon. We're seeing ghosts of objects we can no longer touch. None of these galaxies are breaking the speed of light. Inside their own local region, they're drifting gently through space, the way our own galaxy drifts. What changed is the distance between their patch of space and ours. The space itself grew, a stretching rubber sheet with 2 ants sitting still on it. Pull the sheet hard enough and the ants separate faster than either of them could ever walk. So mission planners started asking the dangerous question. If space can carry galaxies apart at superluminal speeds, can space also carry a spacecraft? The honest answer in principle is yes, and the mechanism does not require new physics. It only requires new engineering, because the way the universe naturally stretches space is through dark energy, a diffuse force spread evenly across the cosmos, and dark energy is not something you can load into a fuel tank. What you would need is a way to locally compress and expand space on demand. Squeeze the region ahead of your ship, stretch the region behind it, sit inside a pocket that moves because the geography around it is shifting, not because the pocket itself is accelerating. From inside the pocket, your onboard clock runs normally. You feel no g-forces because you're not accelerating through space. You're being carried by a wave of warp geometry, like a surfer riding a swell. The swell does the work. The surfer just stands there. From outside, observers watching the ship would see something impossible. A craft arriving at its destination faster than a light beam could have made the same trip. Not because the craft outran light, because the craft took a shortcut that light did not have access to. This is the entire premise of warp drive. Not magic, not science fiction, an engineering application of the same geometry that already carries galaxies beyond our cosmic horizon every second of every day. The question that took 7 decades to crack was whether the math actually permitted a bubble of stretched space to exist without the rest of the universe collapsing on top of it. In 1994, a physicist named Miguel Alcubierre sat down and wrote the equations that said yes. And then the problems began. Log the date. May 1994, a Mexican theoretical physicist named Miguel Alcubierre, then working at the University of Wales, sits down to solve a problem that came to him after watching an episode of Star Trek. He wants to know if the Enterprise, the fictional starship that moves faster than light without breaking relativity, could exist as a valid solution to Einstein's field equations. Most physicists would have written off the question as a joke. Alcubierre treated it as a homework problem. He opened the equations of general relativity, the same equations that describe black holes and the expansion of the universe, and he asked them a precise mathematical question. What shape would space-time need to have in order for a region inside it to move faster than light without any object within that region actually exceeding light speed? The equations answered him. Alcubierre published his result in the journal Classical and Quantum Gravity under the title The Warp Drive, Hyperfast Travel Within General Relativity. It was a short paper, 8 pages. It would become one of the most cited theoretical physics papers of the 1990s. The core idea was elegant. Alcubierre proposed a specific metric, a mathematical description of how space-time curves that creates a bubble. Inside the bubble, space is flat. Everything behaves normally. Clocks tick at the standard rate. Light moves at the standard speed. Crew members inside would feel no forces, no acceleration, nothing unusual. They could sip coffee and play cards. Outside the bubble, space is also flat, matching the ordinary universe around it. But at the boundary of the bubble, space-time is doing something bizarre. On the leading edge, space is aggressively contracting, pulled in toward the ship. On the trailing edge, space is just as aggressively expanding, pushing outward. The bubble itself rides forward on the imbalance. Picture a conveyor belt made of space. The belt contracts in front of the craft and stretches behind it. The craft does not move along the belt moves the craft. From outside, the bubble can travel at any speed whatsoever, including speeds many times faster than light. From inside, the ship is sitting perfectly still. No rule of relativity is violated. The ship is not accelerating. Light can always outpace the ship within the bubble. The speed limit holds locally, exactly as Einstein wrote it. The trick is that the bubble itself is not a thing moving through space. The bubble is a feature of space, and features of space are allowed to move at any speed, just like the expanding universe does at the cosmic horizon. When Alcubierre published, the physics community reacted with a mixture of delight and skepticism. The math was correct. The solution was a valid answer to Einstein's equations, but like many valid solutions in general relativity, it came with conditions that made most physicists deeply uneasy. The warp bubble, as Alcubierre originally designed it, required a substance that no one had ever observed, a substance with properties so strange that mainstream physics was not even sure it could exist. The exact technical term written in the paper was matter with negative mass density. Ordinary matter pulls on space-time, curving it inward, creating the gravity we feel every day. Negative matter would do the opposite. It would push space-time outward, repel it, behave like anti-gravity. To build Alcubierre's warp bubble, a ship would need vast quantities of this anti-gravity substance, arranged in precisely the right shape around the hull, and no one had ever seen a single gram of it. The question became whether it could exist at all. Open the simulation. A warp bubble is a specific geometric deformation of space-time, and the only way to understand it is to picture the shape carefully. Start with a flat sheet of paper. That is space at rest. Draw a small circle in the middle of the sheet. That is your ship. Now imagine that the region just in front of the circle gets scrunched together, compressed until it almost pinches to a point. At the same moment, the region just behind the circle gets stretched outward, expanding like taffy being pulled. The circle itself has not moved on the paper, but the paper around it is now deformed. The compressed region in front is short, the stretched region behind is long. Relative to the unchanged sheet beyond the deformation, the circle has effectively shifted forward, because the space in front of it is shorter than it used to be, and the space behind it is longer. That is the whole principle. Contract space ahead, stretch space behind. Sit inside the pocket that results, and the pocket will translate forward without the ship ever firing a thruster. Alcubierre's mathematical solution described exactly this deformation in 3 dimensions, with precise equations for how the compression and expansion should blend at the edges of the bubble. The bubble has a wall, a shell of curved space-time where the transition happens. Inside that shell, space is flat. Outside, space is also flat. Only the thin shell is doing the work. The crew inside experiences nothing. Because the bubble's interior is flat space, there is no gravitational field, no tidal stress, no sense of motion. An astronaut standing at the window would see the universe outside rush by at any speed the bubble is moving, but their body would register the trip as completely still. No g-forces, no inertia, no need for seatbelts. This is the feature that makes warp drive different from every other propulsion concept. A fusion rocket accelerating to 10% of light speed would crush its crew against the back wall for months. A solar sail pushed by ground-based lasers would take decades to reach useful velocity, every second of it requiring careful shielding against radiation. A warp bubble skips the acceleration phase entirely. You are here, then the bubble forms around you, then you are there. There is a subtlety worth pointing out. The bubble moves through the universe, but the ship does not move through the bubble. The ship is locked to the bubble's interior like a raisin set in bread. When the bread rises, the raisin goes along with it, but the raisin has done no work. Which means the ship carries almost no kinetic energy in the traditional sense. A conventional spacecraft moving at 90% of light speed has colossal momentum. If it hits anything, the impact is apocalyptic. A warp ship, by contrast, is sitting still inside its bubble. Its momentum relative to the space immediately around it is close to zero. The bubble has the momentum, not the ship. That detail matters when you start thinking about how to stop, how to steer, and how to avoid catastrophic collisions with interstellar debris. The bubble is the thing that needs to be steered, the ship is just a passenger. Now the engineering question: how do you actually build a shell of space-time with those exact properties? What physical substance, arranged in what configuration, produces the right curvature on the right surface at the right moment? Alcubierre's paper had an answer. The answer is where the whole project nearly collapsed. Read the fine print. Alcubierre's 1994 paper includes a requirement that most science fiction adaptations conveniently forget to mention. The warp bubble, as originally described, requires matter with negative energy density to hold its shape. What is negative energy density? Ordinary matter, the kind everything around you is made of, has positive energy. A rock has positive energy. A cloud of gas has positive energy. Even empty space, thanks to quantum fluctuations, has a small positive energy density. Everything we can see, touch, or measure falls into this category. Negative energy is the opposite. A substance with negative energy density would exert anti-gravity. Drop a ball of it, and the ball would fall upward. Place it near a planet and the planet would be gently repelled instead of pulled in. It would curve space-time outward instead of inward. Nothing like that has ever been observed in bulk. Every particle ever detected, every field ever measured, every corner of the universe ever surveyed, contains only positive energy. Negative energy is not part of the known material inventory of reality. There is a small exception, and physicists love to mention it. The Casimir effect, a tiny quantum phenomenon that occurs between two closely spaced metal plates in a vacuum, produces a region of genuinely negative energy density. The effect is real. It has been measured in laboratories since 1997. But the amount of negative energy produced is absurdly small, measured in fractions of a trillionth of a joule, confined to a gap the width of a human hair. Alcubierre's warp bubble needs vastly more than that. The original paper estimated the requirement at levels of negative energy comparable to the mass of the planet Jupiter, converted entirely into negative form. That is 10 to the 27th kilograms of substance that nobody has ever seen a single atom of. The physics community split on how to interpret this. Some argued that negative energy in large quantities probably cannot exist. Theorems in quantum field theory, known as the energy conditions, place strict limits on how much negative energy can be concentrated in any region. If those energy conditions are correct, Alcubierre's warp drive is flatly impossible to build. Others pointed out that the energy conditions may not be absolute. General relativity itself does not forbid negative energy. It only describes what would happen if you had some. Quantum mechanics allows small amounts temporarily through effects like the Casimir force. The question of whether large, stable regions of negative energy can exist is still open. For the physics community in 1994, the verdict was cautious but not final. The warp drive was a valid solution to Einstein's equations, but the fuel it needed was a substance that might not exist. Most physicists filed the paper under interesting but impractical. A handful did not. A small group of theorists saw the bubble as an invitation. If the geometry worked, then the question became how to modify the design to need less exotic matter, or none at all. The next 2 decades of warp drive research were entirely devoted to that question, and the numbers slowly started to move. Load the original fuel calculation. When Alcubierre published his paper in 1994, the negative energy requirement was not just large, it was catastrophically large. Physicists who ran the numbers came back with a figure that made the concept look like a mathematical curiosity rather than an engineering project. The early estimate, based on a bubble large enough to carry a small spacecraft, suggested negative energy equivalent to the mass of the entire observable universe. That is not a typo. Every star, every galaxy, every cloud of gas in every direction, all of it converted into negative form. The number was so absurd that many physicists assumed they had calculated wrong. They had not. The original Alcubierre metric was what theorists call energy inefficient. The bubble wall, the thin shell of curved spacetime that does all the work, had to be extraordinarily thin and extraordinarily warped to move faster than light. Each of those requirements ballooned the negative energy demand independently, and multiplied together they produced a figure large enough to consume the cosmos. Later calculations brought the number down. Recomputing with more realistic bubble geometries, physicists estimated the requirement at something closer to the mass of Jupiter. Still impossible. But smaller than the universe, which counted as progress. To put the Jupiter figure in perspective, consider the total mass of everything humanity has ever launched into space. From the first Soviet satellite in 1957 through every space shuttle mission, every Mars rover, every GPS satellite, every private rocket launch, the total payload mass delivered to orbit by all human civilization combined is roughly 20,000 tons. Jupiter weighs 2 trillion tons. The gap between what we can lift and what the original warp drive required is a factor of 100 quintillion, and that is the positive mass of Jupiter. The negative mass version would be something fundamentally stranger, a substance with properties opposite to everything in the solar system, assembled in quantities larger than a gas giant, compressed into a shell around a spacecraft. The theoretical physics community reacted by dividing into 2 camps. The skeptics pointed to quantum energy conditions, mathematical constraints showing that negative energy, when it exists at all, tends to be accompanied by equal amounts of positive energy nearby, cancelling out over any meaningful region. Building a sustained bubble of pure negative energy, the skeptics argued, might be forbidden at a deeper level than general relativity alone could reveal. The other camp pointed to loopholes. The energy conditions are not theorems in the strict sense. They are assumptions that work for ordinary matter but have known exceptions. The Casimir effect is one such exception. Certain quantum fields, particularly around black hole horizons, appear to violate the energy conditions temporarily. If those violations could be scaled up or stabilized, warp bubbles might become feasible. Neither camp could prove the other wrong. The debate stayed open because nobody had the experimental tools to test either position. Lab-scale experiments with Casimir cavities produced negative energy at levels trillions of times too small to measure against warp drive requirements. cosmological observations could not resolve the question at all. What could change, and what did change, was the design of the bubble itself. If the original geometry was inefficient, maybe a smarter geometry would need less fuel. The next generation of theorists went looking for exactly that kind of optimization. The first breakthrough came in 1999, and it did not involve new physics at all, just a cleverer shape. Open the follow-up paper. 5 years after Alcubierre's original publication, a Belgian physicist named Chris van den Broek submitted a paper to the same journal with a small but transformative insight. Van den Broek did not challenge Alcubierre's math. He accepted every equation exactly as written. What he changed was the geometry of the bubble itself. His key move was separating two things most physicists had treated as one: the external size of the warp bubble, meaning how much volume it occupies in the surrounding universe, does not have to match the internal size, meaning how much space is available inside for passengers. In general relativity, these two measurements can be decoupled because space-time is flexible enough to have a tiny exterior wrapped around a large interior. Van den Broek proposed a bubble whose outer surface was absurdly small, on the order of 10 to the negative 15 meters. That is roughly the size of an atomic nucleus, a warp bubble the size of a proton, with a spacecraft sitting comfortably inside a normal-sized chamber of flat space. The idea sounds impossible on its face. How can a spacecraft fit inside a proton? The answer is that general relativity allows the interior volume of a region to differ from what the exterior would suggest. Think of it like a magic suitcase, where the outside stays small but the inside holds as much as you want to pack. The curvature of space-time handles the bookkeeping. By shrinking the exterior to atomic scale, Van den Broek slashed the negative energy requirement by more than 20 orders of magnitude. The number dropped from something like the mass of Jupiter to something closer to the mass of our home star. Still unimaginably large, still well beyond any known technology. But a reduction by a factor of 100 billion is not nothing. The Van den Broek bubble also passed certain quantum energy tests that the original Alcubierre design failed. Specifically, it satisfied what theorists call the weak energy condition, a mathematical criterion that rules out the most problematic kinds of negative energy distributions. The original Alcubierre drive violated this condition flagrantly. The Van den Broek version did not. The trade-off was a new problem. A bubble that's small requires general relativity to remain valid at atomic length scales, and general relativity has never been tested there. At the scale of a proton, quantum effects dominate, and nobody knows for certain whether space-time behaves classically the way Einstein's equations describe. It might not. The experiment has not been done because nobody knows how to do it. The physics community treated Van den Broek's paper as a real result but an incomplete one. He had proven that the energy requirement was not fundamentally locked to the absurd figures of the original design. The number could move, sometimes dramatically, with the right geometric choices. That meant other optimizations might be possible too. Other theorists took up the challenge. A physicist named José Natario proposed a bubble with no space contraction or expansion at all, just a tangential flow of space-time around the ship, like water flowing around a rock in a river. Natario's design sidestepped some of the original pathologies, but introduced new ones. The search continued. By the early 2000s, warp drive theory had become a small but active research field, with papers appearing every year or two, each one shaving a little more off the energy budget or fixing a different technical flaw. The numbers were still impossible, but the trajectory was downward. and the engineering picture was becoming clearer. Then a NASA physicist walked into the conversation with a redesign that changed everything. Switch to a NASA briefing room, 2011. A physicist named Harold White, working at the Johnson Space Center's Advanced Propulsion Laboratory known as Eagle Works, is about to present a reworked warp drive design to the 100-year Starship Symposium. The audience includes engineers, physicists, and a handful of science journalists who have come to see whether the concept is being taken seriously at the space agency level. White does not question whether warp drive is theoretically valid. He accepts Alcubierre's math. What he presents is a geometric optimization that reshapes the bubble itself to minimize the negative energy requirement even further than Van den Broek managed. The key change is the thickness of the bubble wall. In the original Alcubierre design, the wall was thin and sharp, compressing and expanding space-time over a very short distance. That sharpness was part of what drove the energy cost into cosmological scales. White proposed widening the wall, turning the bubble boundary from a thin shell into a thicker, more gradual transition zone. The compressed region in front and the stretched region behind would still do their work, but the gradient would be softer, spread over a larger area. He also changed the bubble's cross-section. Instead of a sphere, White's version was shaped like a donut, a torus, with the ship riding through the center hole. The torus geometry concentrated the warping in specific regions and left other regions relatively untouched, further cutting the integrated energy requirement. When White ran the numbers on this redesigned bubble, the result was astonishing. The negative energy requirement dropped to roughly the mass of a large NASA probe, on the order of 700 kilograms if the exotic matter could be produced in pure form. 700 kilograms is the mass of a small motorcycle. Compared to Jupiter or the observable universe, that is an almost trivial fuel budget. The catch, of course, was that negative energy still had to exist and had to be concentrated into that 700 kilogram reservoir. The redesign did not solve the fundamental problem. It just made the problem smaller by a factor of many trillions. White went further. He proposed that Eagle Works could run small-scale laboratory tests to look for microscale space-time warping using a modified Michelson interferometer, a device similar in principle to the instruments that later detected gravitational waves at LIGO. The experimental setup, if it worked, would measure the faint curvature of space-time around charged capacitor rings under specific voltage conditions. The experiment ran. The results were ambiguous. Eagle Works reported some anomalous interferometer readings, but the signal was too weak and too noisy to distinguish from ordinary experimental error. Critics pointed out that the lab's conditions were not controlled tightly enough to rule out thermal effects, air currents, or electromagnetic interference. NASA never formally claimed that warp field effects had been detected. The scientific community remained divided. Some physicists treated White's work as over-optimistic, arguing that the theoretical energy reductions, while mathematically valid, still relied on negative energy that probably cannot exist in sustained form. Others saw the work as a legitimate engineering direction, even if the current numbers were impractical. The fact that NASA, the largest space agency on Earth, was funding the research at all gave the field a legitimacy it had lacked before. Eagle Works eventually pivoted to other projects, but White's geometric optimizations remain part of the warp drive literature, and every subsequent theorist has built on the thicker wall-shaped bubble approach he formalized. The energy budget had dropped, the bubble was reshaped, and yet two deeper problems, quieter but more serious, were waiting in the equations nobody had fully solved. Bring up the causal diagram. When an object moves through space at less than light speed, information can flow freely in every direction around it. Signals from the front, signals from the back, signals from the sides, all of them reach the object in predictable time. This is the baseline condition for controlled flight. You can see where you're going, communicate with your destination, and respond to threats. A warp bubble moving faster than light breaks this baseline in a way that did not become clear until theorists examined the geometry in detail. Here is the problem. The front wall of a superluminal bubble is moving outward faster than any light beam from inside the bubble could ever reach it, which means the interior of the ship is causally disconnected from its own leading edge. A signal sent from the pilot's seat to the front of the bubble would never arrive, because the front is racing away faster than the signal can chase. In technical terms, the bubble creates a horizon, the same kind of horizon that surrounds a black hole, where light cannot escape because space-time is falling inward faster than light can climb out. A warp bubble generates its own event horizon on its leading surface, and anything inside the bubble cannot influence anything outside the bubble in the forward direction. This has severe consequences for the pilot. During the entire voyage, the ship cannot steer, cannot adjust course, cannot transmit any signal ahead of its own position. The bubble, once launched, must be set up with its full trajectory pre-programmed, because the crew inside has no causal access to the region of space the bubble is moving into. It gets worse. A warp bubble cannot be stopped from inside either. To decelerate, the bubble would need to change its own geometry, which requires an external agent operating at the destination, or some mechanism embedded in the bubble wall that can run autonomously once the voyage begins. The pilot sitting in the control seat is effectively a passenger in a sealed container, watching the universe go by through windows that no longer obey the normal rules of communication. Theorists have proposed solutions. One idea is to seed the destination with some kind of beacon or receiver before the warp ship arrives, set up by earlier subluminal missions. The receiver could collapse the bubble on arrival using pre-positioned equipment, ending the voyage on command. This is workable for planned routes but useless for exploration, because you cannot send a warp ship anywhere that does not already have infrastructure waiting. Another idea involves oscillating the bubble, switching it on and off at high frequency so that the ship has causal contact with the outside universe in between pulses. The math for this has been worked out in some models, but it introduces stability problems that nobody has solved. A bubble that keeps collapsing and reforming may emit catastrophic bursts of radiation each cycle. The horizon problem is not a showstopper in the way the negative energy problem is. It does not say warp drive is impossible. It says warp drive, if it works, would be a very different kind of vehicle than anyone imagined. Not a steerable starship, but a ballistic projectile, aimed before launch and unable to change course in flight. For a crewed mission to another star, this is a serious mission constraint. Any error in the initial trajectory cannot be corrected. Any hazard along the route cannot be avoided. The ship arrives where the bubble takes it, or it does not arrive at all. And there is a second consequence of the horizon, discovered by theoretical physicists studying quantum effects near black holes, that is far worse than losing steering control. A horizon is where radiation comes from. Pull up the thermodynamics textbook. In 1974, Stephen Hawking proved a result that stunned the physics community. Black holes, which everyone had assumed were perfectly cold and absolutely silent, actually emit a faint glow of radiation. The glow comes from quantum effects right at the event horizon, where pairs of virtual particles constantly pop into existence and annihilate again. Near an event horizon, this balance breaks. One particle of the pair can fall inward, while the other escapes outward, carrying energy away from the black hole. Over cosmic timescales, this slow leak causes black holes to evaporate. The effect is named Hawking radiation, and its discovery remains one of the deepest results in modern physics. Now apply the same analysis to a warp bubble. Because the bubble's leading edge forms its own horizon, the same quantum process should occur there. Pairs of virtual particles near the front wall get separated, with one falling inward toward the ship and the other escaping forward. The ship, sitting inside the bubble, is now being irradiated by a steady stream of particles generated by the horizon geometry itself. The problem is worse than for a black hole. Real black holes are enormous, and their Hawking radiation is faint. A black hole the mass of our home star emits radiation at a temperature of about 60 nanokelvin, so cold it is effectively undetectable against the cosmic microwave background. A warp bubble, by contrast, is much smaller, and the radiation temperature scales inversely with the horizon's radius of curvature. A smaller horizon means hotter radiation. Theoretical calculations suggest that a warp bubble travelling at superluminal speeds would generate a horizon temperature thousands or millions of times hotter than a comparable black hole. The interior of the ship would be bathed in high-energy particles pouring inward from the leading wall. The crew would not just die, they would be cooked at temperatures that exceed the surface of our nearest star, possibly within seconds of bubble formation. A paper published in 2009 by physicists at the University of Sydney ran this calculation in detail. Their conclusion was stark. Any macroscopic warp bubble travelling faster than light would generate Hawking-like radiation at the front wall intense enough to vaporize the spacecraft before it completed even a fraction of a second of flight. The faster the bubble, the hotter the radiation, the quicker the destruction. There are possible workarounds. If the bubble wall is carefully shaped, some of the radiation might be redirected away from the ship rather than inward. If the bubble moves at slightly subluminal speeds, no true horizon forms, and the Hawking effect does not apply. Alcubierre himself speculated that quantum gravity corrections, the still unknown physics that merges general relativity with quantum mechanics, might soften the effect in ways his original paper did not account for. None of these workarounds have been rigorously demonstrated. The horizon radiation problem remains one of the most serious theoretical objections to warp drive, and it is not the kind of problem that better engineering can solve. It is built into the geometry itself. A faster-than-light bubble generates a horizon. A horizon generates radiation. The radiation lands on the ship. For mission planners, this is an unusual kind of threat. Most spacecraft hazards can be shielded against. Cosmic rays can be blocked by enough water or lead. Micrometeorites can be deflected by Whipple shields. Hawking radiation from a warp horizon is generated by the very space-time the ship is riding inside, and there is nowhere to put the shielding that would not disrupt the bubble. The problem is not the only one with the leading edge. There is another hazard, less exotic but just as dangerous, involving what happens to any ordinary matter the bubble collides with during flight. Check the collision model. Interstellar space is not empty. It is thinly populated with hydrogen atoms, helium atoms, occasional grains of dust, rare micrometeorites, and cosmic rays streaming in from distant supernovae. The density is low, roughly 1 atom per cubic centimetre in the interstellar medium. For a slow-moving spacecraft, this density is negligible. For a warp bubble moving at hundreds or thousands of times the speed of light, it becomes catastrophic. The physics was worked out in a paper by Brendan McMonagle, Geraint Lewis, and Philip O'Byrne at the University of Sydney in 2012, the team asked a specific question: what happens to the hydrogen atoms and dust grains that the warp bubble sweeps up during its voyage? Where do those particles go, and with what energy? The answer was alarming. As the bubble moves forward, ordinary matter in its path gets caught in the leading edge of the warping region. These particles do not pass cleanly through. They accumulate at the front wall, accelerated by the compression of space-time, building up a reservoir of trapped matter that travels along with the bubble. The reservoir grows the longer the voyage continues. When the bubble arrives at its destination and switches off, all the accumulated matter gets released at once. The trapped particles, now carrying energies equivalent to hundreds of thousands of solar masses worth of kinetic energy, blast outward from the ship's position in a concentrated beam. The beam goes in the direction the ship was travelling, which is, by design, toward the destination. A warp ship arriving at Proxima Centauri would not land gracefully. It would unleash a wavefront of high-energy radiation powerful enough to sterilize any planet in the target system. The beam would be narrow, focused by the bubble's geometry, and utterly devastating to anything directly in its path. The ship itself would survive the arrival. The star system ahead of it would not. This is the interstellar equivalent of showing up to a diplomatic meeting with a loaded howitzer pointed at the host. Any civilization receiving a warp ship would register the incoming beam long before the ship arrived and would have no way to distinguish a peaceful mission from an attack. The visual signature would be identical. The Sydney team also noted that even microscopic amounts of absorbed matter could produce the effect. The bubble does not need to sweep up a planet's worth of gas to become dangerous. Even the extremely thin medium of deep interstellar space provides enough hydrogen and dust over a multi-light-year voyage to accumulate a beam with planet-killing energy. Proposed workarounds exist. Some designs suggest a bubble geometry that deflects incoming particles around the ship rather than trapping them, essentially a hydrodynamic smoothing of the front wall. Other designs propose ending the voyage at a safe distance from the destination in empty space, allowing the beam to disperse harmlessly before the ship completes its approach under normal propulsion. Both ideas add mass, complexity, and new failure modes. For mission planners, the debris problem changes how warp ships would have to be used. They could not approach inhabited systems directly. They could not decelerate suddenly near any object of interest. They would need a specific arrival protocol involving long deceleration corridors and careful alignment of the exit beam away from any target worth visiting. Between the horizon, the radiation, and the debris beam, the original Alcubierre warp drive started looking less like a starship and more like a loaded weapon that accidentally transports its crew. But theoretical physics is patient, and a generation of researchers who grew up reading Alcubierre's paper were about to propose a very different kind of warp bubble. Open the Göttingen paper, March 2021. An American physicist named Eric Lentz, working at the University of Göttingen in Germany, submits a paper with a claim that most of the warp drive community considered impossible. Lentz argues that a warp bubble can be constructed using only positive energy, no negative energy, no exotic matter, nothing that violates the classical energy conditions. The claim, if correct, would be one of the most significant results in theoretical physics since Alcubierre's original paper. For 27 years, every warp drive design had depended on negative energy in some form. Every paper, every optimization, every reduction of the fuel requirement had only managed to shrink the amount of exotic matter needed, not eliminate it. Lentz proposed to eliminate it entirely. His approach was mathematical rather than geometric. Instead of starting with a bubble shape and asking what matter distribution would hold it together, Lentz started with a new kind of solution to Einstein's equations called a soliton. In physics, a soliton is a stable, self-reinforcing wave that maintains its shape while moving through a medium. Ocean waves usually spread out and flatten. Solitons do not. They travel as compact, coherent packets that can cover long distances without losing structure. Lentz asked whether space-time itself could support soliton solutions that would carry a region of flat space along with them, behaving like a warp bubble, but without requiring negative energy densities anywhere in the structure. His mathematics said yes. The resulting metric described a hyper-fast soliton, a bubble of warped geometry moving at any speed, subluminal or superluminal, held together by ordinary positive energy arranged in a specific plasma-like configuration. The paper, titled Breaking the Warp Barrier, Hyperfast Solitons in Einstein-Maxwell Plasma Theory, landed with a significant impact in the specialist community. News outlets picked it up with headlines suggesting that warp drive was finally possible. Some physicists agreed, others immediately pushed back. The main criticism came from theorists who re-examined Lentz's math and argued that his solution might not be as free of negative energy as he claimed. Under certain coordinate transformations, the energy distribution in Lentz's soliton could be rewritten in ways that made negative energy reappear. The debate was technical, hinging on how one defines physicality across different reference frames in general relativity. Lentz defended his result. He pointed out that in the co-moving frame, the frame of reference riding along with the bubble itself, the energy densities were all positive, which meant that no observer travelling with the ship would encounter anything unphysical. Other frames might see the numbers differently, but that was a feature of relativity, not a flaw in the solution. The debate has not been resolved in the years since. Some physicists accept Lentz's solution as a legitimate positive energy warp drive. Others treat it as a clever reformulation of the same old problem in different coordinates. The question of whether true positive energy warp bubbles exist in the rigorous mathematical sense is still active research. What Lentz did unambiguously accomplish was reopening a question that the community had largely closed. For decades, the assumption had been that warp drives required exotic matter, full stop. After Lentz, that assumption became a debate again, and once a debate reopens in theoretical physics, new papers follow. A few months later, a different pair of researchers published their own framework for classifying warp drive spacetimes. Their result would change how the entire field approached the problem. Pull up the framework paper. February 2021. Two researchers, Alexei Bobrik and Gianni Martir, working with a private research organisation in New York called Applied Physics, publish a paper titled Introducing Physical Warp Drives. The paper does not propose a specific warp drive design. It does something more ambitious. It proposes a general classification scheme for every possible warp drive spacetime, a taxonomy that defines what any warp drive must contain and how different designs relate to each other. The core insight is simple in retrospect. Bobrik and Martir argue that every warp drive, without exception, consists of three regions: an asymptotically flat vacuum region far from the ship, matching the ordinary universe, a passenger region at the centre, also flat, where the crew lives, and a warping region in between, the shell of curved space-time that does the work of moving the bubble. Every warp drive ever proposed, from Alcubierre's original design to Van den Broek's shrunken bubble to White's thickened wall to Lentz's plasma soliton, fits into this three-region framework. The differences between them come down to how the warping region is shaped, what kind of matter fills it, and how the bubble interfaces with the outside universe. This may sound like bookkeeping, but it had immediate consequences. Once all warp drives were mapped into the same framework, Bobrick and Martyr could ask systematically which regions of the design space had been explored and which had not. They found large territories that no previous paper had investigated. One of those territories was the Subluminal warp drive. Most previous research had focused on superluminal designs, because superluminal was the whole point of warp drive. Bobrick and Martyr pointed out that subluminal warp drives, bubbles moving at less than the speed of light, might be much easier to build. They might satisfy the energy conditions. They might not require exotic matter at all. More importantly, Bobrick and Martyr proved a theorem that had not been explicitly stated before. Any warp drive spacetime, regardless of its design, is effectively a shell of matter that has been set in motion. The shell moves inertially, like any other chunk of matter in the universe, which means it still needs some conventional propulsion system to accelerate it to its cruising speed in the first place. A warp bubble does not eliminate the need for rockets, it just changes what the rocket is pushing. This result reframed the entire engineering problem. Warp drive was not magic. It was a specific kind of structured matter that, once set in motion, carried a region of flat space along with it. The internal crew felt no G-forces. The external universe saw the bubble move. But getting the bubble up to speed in the first place still required conventional physics. The paper also included extensive analysis of the negative energy problem, showing that certain subluminal warp drives satisfy the weak energy condition and require no exotic matter. The authors were careful not to overclaim. Their paper did not solve the superluminal problem, but it cleared a path toward building subluminal warp bubbles with known physics, something that had been considered marginal before 2021. Bobrick and Martyr's framework became the standard reference for the next wave of warp drive research. Papers following theirs cite them heavily, and their classification is now used to describe new designs. The two researchers, along with their colleagues at Applied Physics, had positioned themselves at the centre of a small but serious scientific enterprise. The real engineering push was about to begin. Switch locations: 477 Madison Avenue, New York City. An office building in Midtown Manhattan hosts the headquarters of a research organization called Applied Physics, operating an internal division known as the Advanced Propulsion Laboratory. Unlike NASA Eagle Works or a university physics department, Applied Physics is a private entity. It funds its own research, employs its own scientists, and publishes in mainstream journals like Classical and Quantum Gravity. The team is small, under a dozen core researchers, led by Gianni Martir, the co-author of the 2021 framework paper. The scientific staff includes Alexei Bobrick, the other co-author, a physicist named Jared Fuchs, originally trained at the University of Alabama in Huntsville, Christopher Helmerich, another Alabama alumnus, Luke Sellers, Brandon Melcher, a handful of affiliated researchers at partner institutions. Their mission, as described in public statements, is to treat warp drive as an engineering problem rather than a theoretical curiosity. The difference matters. A theorist studies whether warp drive is mathematically consistent. An engineer studies how to build one, what materials would be needed, what instruments could detect the space-time curvature it produces, and what sequence of experiments could incrementally verify the concept. Applied Physics pursues both threads. On the theoretical side, the team publishes papers refining the mathematics of warp spacetimes, classifying solutions, and proving new no-go theorems where applicable. On the engineering side, they have developed software tools, experimental proposals and instrument designs that treat warp drive as a problem to be built, not just analysed. One of their most significant practical contributions is a software package called Warp Factory. Written in MATLAB, Warp Factory allows physicists to input any proposed warp drive metric and numerically evaluate its properties. The tool calculates the curvature, the stress energy tensor, the energy conditions, and the gravitational signatures produced by the configuration. Before Warp Factory, these calculations had to be done by hand for each new design, which limited how thoroughly any individual paper could explore the solution space. With the tool, researchers can scan thousands of candidate designs in a reasonable time. The team has also proposed experimental techniques for detecting warp drive activity at astronomical distances. If an advanced civilization anywhere in our galaxy were operating warp ships, the space-time disturbances they produce might be observable as gravitational wave signatures, detectable with future instruments. Applied Physics has submitted proposals arguing that current and next-generation gravitational wave observatories should include warp drive signals in their search templates. Critics of the organization raise several concerns. Applied Physics is privately funded and operates outside the traditional academic structure, which some researchers view as reducing its accountability. The lab has produced press releases describing its work in language that sometimes overstates how close warp drive is to practical reality. Some mainstream physicists worry that the media attention the lab generates outpaces the scientific progress. Defenders point to the peer-reviewed papers. Applied physics researchers publish in respected journals. Their work passes external review. Their results cite carefully and critique themselves. Whatever one thinks of their public messaging, the technical output is real. And in 2024, the Applied Physics team released a paper that represented the most significant advance in warp drive theory since Alcubierre's original work 30 years earlier. For the first time, they claimed a complete warp drive solution, requiring no exotic matter at all. Load the breakthrough publication. Classical and Quantum Gravity, Volume 41, Article 95013, published April 29, 2024. Title: Constant Velocity Physical Warp Drive Solution. Lead author Jared Fuchs. Co-authors include Helmerich, Bobrick, Sellers, Melcher and Martyr. The entire Applied Physics team pulling in the same direction on a single problem. What the paper claims is extraordinary. The authors present a warp drive solution that satisfies all of the energy conditions. Every one of them. The weak energy condition, the null energy condition, the dominant energy condition, the strong energy condition. No negative energy anywhere in the structure. No exotic matter. No violations of any principle that has been observed in nature. The design they describe combines two elements: a stable matter shell with a specific density distribution, built entirely from positive energy material, of the kind that exists throughout the ordinary universe, and a shift vector distribution, a mathematical feature of space-time that closely resembles the Alcubierre bubble geometry. Together, the shell and the shift vector produce a warp effect. A region of flat space moves through the surrounding universe, carrying anything inside it along for the ride. The paper uses Warp Factory, the team's own simulation software, to evaluate the configuration numerically. The software shows a blue region, representing positive energy density, filling the entire warp shell. Black lines representing momentum flux show the structure of the bubble's internal dynamics. Nowhere in the visualization does the red color appear that would indicate a violation of physical constraints. The drive, as modeled, is clean. Fuchs, in the official press release accompanying the paper, explained the breakthrough plainly. Prior models, he said, required matter and energy content that was unphysical, meaning it had features nobody has ever observed in the regular universe. The new approach avoided that by adding positive energy to the solution, while keeping as much of the warp effect as possible. When physicists talk about positive energy, Fuchs noted, they mean phenomena like light, matter, and antimatter, all of which exist naturally and abundantly. The solution also proposes that gravity itself can be used to warp space-time, alongside the positive energy in the shell. This is not a contradiction. Gravity is the manifestation of curved space-time in the first place. A sufficiently dense and precisely shaped distribution of ordinary matter curves the space around it, and that curvature, when combined with the shift vector structure, produces the warp bubble geometry. But the paper includes a caveat that the headlines often left out. This solution is explicitly subluminal. Constant velocity. The bubble moves at a fixed speed slower than light. It does not solve the faster than light problem. It solves a different problem, one that Bobrick and Martyr had identified in their earlier framework. It demonstrates that warp spacetimes, as a class, are not inherently dependent on exotic matter. At least some warp configurations can be built from ordinary materials, operating within known physics. Fuchs himself was careful about this limitation. He told reporters that the concept will not deliver the Star Trek-like future of rapid interstellar transport. What it does deliver, he said, is the warp effect of accelerating passengers without any g-forces using regular matter. That capability, even at subluminal speeds, could lead to other kinds of interesting things. The scientific reception of the paper was mixed but generally positive. Mainstream physicists acknowledge that the solution is mathematically valid, satisfies the energy conditions as claimed, and represents a genuine step forward in the field. Skeptics pointed out that a subluminal warp drive, while technically novel, does not solve the interstellar travel problem because ordinary rockets can already move at subluminal speeds, and the energy cost of building the precisely shaped matter shell would still be astronomical. The question left hanging was whether the same mathematical techniques could be extended to superluminal regimes. The authors did not claim they could. Other researchers started asking whether they might. Open the software toolkit. Alongside their theoretical papers, the applied physics team released a tool that changed how warp drive research gets done. The tool is called Warp Factory. It is written in MATLAB, the same numerical computing environment used by engineers across the aerospace industry, and it is freely available to any physicist who wants to download it. Before Warp Factory existed, evaluating a proposed warp drive metric was brutally labour-intensive. A researcher would write down the mathematical description of a bubble, then spend weeks or months calculating by hand what kind of matter would be needed to produce that geometry, whether the energy conditions held, and what gravitational effects the bubble would generate. Each new design required a fresh round of calculations. Mistakes were common. Comparison between designs was nearly impossible, because different papers use different notation and different assumptions. Warp Factory fixes that. A user inputs the metric, the mathematical description of the spacetime curvature. The software then computes everything else automatically. The stress energy tensor, which tells you what kind of matter would be needed. The energy conditions, which tell you whether that matter is physically reasonable. The curvature scalars, which describe how strongly spacetime is bending. Two-dimensional and three-dimensional visualizations, which let researchers actually see what a warp bubble would look like as a geometric object. The tool uses color coding to make the physics visible at a glance. Blue regions indicate positive energy density, the kind that matches ordinary matter. White regions indicate zero energy, vacuum conditions. Red regions indicate negative energy, the exotic matter that most designs require and that nobody has ever observed in bulk. A warp drive designer can now look at a candidate metric and immediately see which parts of the bubble are physically reasonable and which parts would need unobtainable substances. This capability had immediate consequences for the field. The 2024 Fuchs paper, the constant velocity solution that satisfies all energy conditions, was developed using Warp Factory extensively. The team ran thousands of candidate designs through the software, tuning the matter shell distribution and the shift vector parameters until they found a configuration where no red appeared anywhere in the visualization. Without the tool, finding that specific configuration by hand calculation might have taken decades. Warp Factory also makes it possible to evaluate older designs more rigorously. Researchers have already run the original Alcubierre metric through the software and confirmed exactly how much negative energy the 1994 design actually requires. They have evaluated Vandenbroek's shrunken bubble, White's thickened wall, and Lenz's plasma soliton, producing standardized comparisons that the literature never had before. Some designs passed their own authors' claims, others did not. The software has also become a teaching tool. Graduate students studying general relativity can now experiment with warp drive metrics directly, without needing to reproduce the calculations from scratch. This has broadened the research community significantly. Warp drive theory used to be a specialist subfield, with maybe a few dozen active contributors worldwide. Warp Factory has pushed that number up. Applied Physics has released the code under an open license, and it is hosted on public repositories for anyone to download. The team regularly updates it with new features, responding to requests from users. Researchers in Germany, Australia, Japan, and the United Kingdom have contributed modifications and extensions. One feature the software does not have and cannot have is a way to simulate how a warp bubble actually forms. The tool evaluates static and constant velocity spacetimes. The dynamic process of switching a bubble on, accelerating it, decelerating it, and shutting it down requires a different class of simulation called numerical relativity, which is far more computationally expensive. That kind of simulation is where other teams have been focusing their work, and the results those teams have produced contain their own surprises. Review the limitation honestly. The Fuchs paper represents a real advance in warp drive theory. The solution is mathematically valid, uses only positive energy, and satisfies every known physical constraint. But the press coverage that followed its publication often blurred an important detail, and understanding that detail is essential for any mission planner considering the technology. The 2024 warp drive is subluminal. The bubble moves at a constant speed, and that speed is less than the speed of light. This matters enormously. The original dream of warp drive, going back to Alcubierre's paper, was breaking the light barrier, reaching Proxima Centauri in weeks instead of decades, crossing the galaxy in human lifetimes. The Fuchs design does none of that. A constant velocity subluminal bubble travels the same speed as a conventional rocket, in principle. It takes the same centuries to reach the nearest star. The warp effect provides certain engineering advantages, which we will unpack in the next chapter, but it does not shorten the trip. Why does the subluminal limit exist in this design? The short answer is that crossing the light barrier, in a warp drive context, is what forces the negative energy requirement back into the equations. Every design that moves faster than light generates a horizon at its leading edge, and horizons, for reasons rooted deep in general relativity, tend to demand exotic matter to hold them stable. Subluminal bubbles do not generate horizons, which is exactly why they're easier to build, and also why they do not solve the problem anyone cares about. Fuchs himself was clear about this in interviews. The new model does not deliver rapid interstellar transport. What it does is prove that warp spacetimes as a class of solutions are not inherently unphysical. At least some members of the family can be built from ordinary matter. That is a meaningful result. It just is not the result the headlines promised. The question researchers are now asking is whether the same techniques, the stable matter shell, the carefully shaped shift vector, the positive energy distribution, can be extended to superluminal regimes. The answer is unclear. Some theorists think extension is possible with additional refinements. Others think the light barrier is a genuine wall that no positive energy design can cross, and that faster-than-light warp drive will always require exotic matter, even if subluminal designs do not. The applied physics team has been cautious in their public statements. They have not claimed that a superluminal positive energy solution exists. They have said that their framework leaves the door open to further research in that direction, and that Warp Factory can be used to search the solution space systematically. Some candidate designs have been explored. None have yet produced a superluminal bubble that is fully clean of negative energy under rigorous analysis. Skeptics have pointed to a body of mathematical theorems developed by physicists like Matt Visser, Jessica Santiago and Sebastian Schuster that argue superluminal warp drives must violate the null energy condition regardless of how they are designed. These are called no-go theorems, and they rest on general properties of Einstein's equations rather than on any specific metric. If the no-go theorems are correct in full generality, then no amount of engineering cleverness will produce a superluminal warp bubble without exotic matter. The debate is active. The no-go theorems make assumptions that some physicists consider too strong. The positive energy designs rely on features that some physicists consider too specialized. The truth is likely to emerge slowly, through years of additional papers, additional simulations, and eventually, if the field progresses far enough, through experiments. For now, the honest mission brief is this. Warp drive as a physical effect exists in the equations. Warp drive as a subluminal engineering concept is closer than it has ever been. Warp drive as a faster-than-light interstellar vehicle remains on the wrong side of a wall that nobody has yet figured out how to climb, which does not mean subluminal warp drives are useless. They have one feature that makes them worth building even without superluminal speeds. Open the Human Physiology Report. When a spacecraft accelerates, the crew feels a force. Stand at the back of a rocket climbing at 3 gravities, and every part of your body weighs 3 times what it does on Earth. Your heart has to pump harder, your lungs have to work harder, standing up becomes difficult. Sustained acceleration above about 4 gravities causes most humans to black out within minutes, as blood drains from the brain toward the feet. This is why chemical rockets to orbit are such a brutal experience for astronauts. The 3.5-minute burn of a Falcon 9 puts crew members at roughly 3 gravities for much of the ascent. Space shuttle missions maxed out around 3 gravities as well. Longer or harder burns, the kind you would need for rapid interplanetary travel, are physiologically dangerous. A 10-gravity burn lasting even a few minutes would kill an untrained crew. This constraint shapes every mission plan. To reach Mars quickly, say in 1 month rather than 6, a ship would need to sustain high thrust for long periods, which would require either more efficient engines or a crew made of people who can tolerate sustained high gravity. Neither option exists with current technology. human biology puts a hard cap on how fast we can accelerate, and that cap forces missions to take longer than the engines would otherwise allow. A warp bubble eliminates this constraint entirely. Inside the bubble, space is flat. The crew experiences no acceleration, even if the bubble itself is changing speed rapidly. Because the ship is not moving through space, the crew's bodies do not register any inertial forces. A warp bubble could go from standstill to near light speed in seconds, and the crew inside would feel as if they were sitting on a park bench on a still afternoon. For a subluminal warp drive, this changes the economics of interplanetary travel dramatically. A Mars mission using a conventional rocket requires a carefully planned coast phase, where the engines shut off and the ship drifts for months under zero gravity, because sustained thrust would exhaust the propellant too fast and crush the crew. A warp bubble could maintain constant high acceleration the entire trip, turning a 6-month Mars transit into a matter of days, without any physiological consequence for the passengers. The same logic applies to missions further out. A voyage to Jupiter using conventional propulsion takes several years, partly because of fuel constraints, and partly because the crew cannot tolerate the acceleration required to go faster. A subluminal warp ship could make the same trip in weeks, accelerating steadily to high fractions of light speed and decelerating just as steadily at the destination, with the crew unaware of any of it. Even interstellar missions become more feasible, though not dramatically so. A subluminal warp bubble cruising at 90% of light speed would reach Proxima Centauri in roughly 4.5 years, as measured by outside observers. For the crew, time dilation would shorten the experience duration to about 2 years. That is still a long trip, but it is no longer generational. It is within the career span of a single set of astronauts. There is also a safety benefit most reports overlook. A subluminal warp bubble does not generate a horizon at its leading edge, which means it does not produce the Hawking-like radiation that plagues superluminal designs. It does not trap interstellar particles into a destination sterilizing beam. It does not lose causal contact with its own pilot. All the nastiest failure modes of superluminal warp drive are features of the light barrier itself, and a subluminal ship simply does not cross that barrier. The engineering challenge remains enormous. Building a matter shell with the required density profile, holding it stable in the right geometric configuration, and accelerating the whole structure to cruising velocity are problems that dwarf anything aerospace has ever attempted. The energy cost alone, while far lower than the original Alcubierre design, is still far beyond current capabilities. Nobody is building a warp ship in this decade, or the next. But the physics permits it. The math is clean, the materials are ordinary, the crew is safe. And a new paper in 2026 suggested that the next refinement might be closer than expected. Open the most recent publication, early 2026. A follow-up study from the applied physics team and collaborators revisits the warp drive metrics of the previous 5 years with a sharper set of mathematical tools. The paper's central finding is that space-time can bend further than earlier models assumed, opening design regions that previous researchers had dismissed as physically impossible. The result builds on a specific insight. Earlier warp drive calculations made assumptions about how the bubble's geometry must blend into the surrounding universe. Assumptions rooted in practical convenience rather than physical necessity. When those assumptions are relaxed, the equations permit a wider range of curvature profiles than anyone had previously mapped. Some of those new profiles correspond to warp drives that use even less energy than the 2024 design. A few might allow superluminal operation with significantly reduced exotic matter requirements. The paper does not claim to have solved the superluminal problem. What it claims is that the solution space is larger than the field has been exploring. For 30 years, warp drive research had been narrowing its focus, eliminating candidate designs one by one as they failed various energy conditions or stability checks. The new result argues that some of those eliminations were premature, and that reopening the discarded regions of the design space could yield solutions that combine the best features of multiple earlier models. The implications are still being worked out. Research groups at multiple institutions are now running warp factory simulations on the newly identified metric families, checking which ones satisfy energy conditions, which ones are stable against perturbations, and which ones could plausibly be built with materials that might actually exist. The work is ongoing. No single paper has yet delivered a superluminal warp drive that passes every test. What has changed, subtly but significantly, is the attitude of the broader physics community. Throughout the 1990s and 2000s, warp drive research was treated as a fringe pursuit, tolerated in the literature but rarely discussed at mainstream conferences. By the mid-2020s, papers on physical warp drives were appearing regularly in Classical and Quantum Gravity, Physical Review D, and other respected journals. Conference sessions on the topic drew standing room audiences. Graduate students cited warp drive theory in their dissertations without professional stigma. This shift reflects real progress. The field has moved from mathematical fantasy to engineering problem, even if the engineering is still centuries from practice. Each new paper maps more of the territory, eliminates more dead ends, and occasionally opens new corridors. The trajectory is clear. Whether the trajectory leads to faster-than-light travel or stalls out at subluminal capabilities is not yet known. There is one aspect of the 2026 work that deserves attention. The paper explicitly addresses the stability question. A warp bubble is a dynamic object. It has to be formed, maintained, and eventually dissipated. Earlier designs often assumed stability without proving it. The new framework provides tools for analyzing whether a given bubble geometry will hold together under small perturbations, or whether it will collapse catastrophically the moment it is disturbed. The answer varies by design. Some warp bubbles appear to be stable, others are fragile, prone to failure modes that would tear them apart within microseconds. The distinction matters for any eventual engineering effort. A ship built around an unstable metric would never reach its destination. It would collapse in transit, possibly violently, and that collapse, it turns out, would be detectable across the galaxy. But before we get to detection, there is a rival approach to faster-than-light travel that does not involve warping space in motion at all. An approach that takes a much more radical shortcut through the fabric of the universe. Switch mission concepts. Instead of compressing space in front of a ship and expanding it behind, consider a different approach entirely. What if you could cut a tunnel directly through space-time, connecting two distant points along a path shorter than the surrounding universe allows? The ship does not need to move fast at all. It just walks through the tunnel, emerging light years away moments later. This idea is called a wormhole, and it is the other major candidate for faster-than-light travel that does not break general relativity. Like warp drive, wormholes emerge from Einstein's equations as valid solutions. Like warp drive, they come with serious engineering problems. Unlike warp drive, they require topology changes in the fabric of space-time itself, which makes them arguably even stranger than bubbles of warped geometry. The basic concept was first written down by Einstein and his collaborator Nathan Rosen in 1935. They described what they called a bridge, a connection between two otherwise separate regions of space-time. The Einstein-Rosen bridge, as it became known, was a mathematical feature of black hole solutions, linking the interior of a black hole to a hypothetical other universe or distant region. Early physicists treated this as a curiosity of the math, not a real physical possibility. The situation changed in 1988. Kip Thorne, a Caltech physicist who would later win a Nobel Prize for detecting gravitational waves, published a paper with his collaborators Michael Morris and Ulvi Yurtseva titled Wormholes in Spacetime and Their Use for Interstellar Travel. The paper was partly inspired by a request from Carl Sagan, who was writing the novel Contact, and wanted to know what a scientifically plausible faster-than-light travel mechanism might look like. Thorne's team treated the question seriously. Their result was striking. Thorne showed that traversable wormholes, tunnels that a spacecraft could actually travel through without being destroyed, were valid solutions to Einstein's equations, provided that certain exotic conditions were met. A ship could enter one mouth of the wormhole, travel through a short throat region, and emerge from the other mouth at a location that might be light years distant. The journey could take an hour. The destination could be across the galaxy. Picture a rubber sheet representing space. Place two small weights on the sheet, far apart from each other. Normally, to get from one weight to the other, you would travel across the surface of the sheet, following the long path between them. A wormhole would be a tube drilled through the thickness of the rubber, connecting the two weights directly. The tube is shorter than the surface path because it does not follow the sheet's geometry, it cuts underneath. The trip through the tube does not exceed the speed of light locally. A photon racing through the wormhole would still move at light speed through the throat, but the shortcut makes the effective travel time much shorter than going around. An observer on the outside would see a ship disappear into one mouth and reappear almost instantly at the other, potentially arriving before any light signal following the normal route could make the trip. Unlike warp drive, wormholes do not require moving through the ship's environment at all. There is no bubble, no horizon, no compression or expansion of surrounding space. The tunnel exists as a stable feature of space-time with fixed entry and exit points, and the ship simply flies through. The mouths could, in principle, be positioned anywhere in the universe, provided that something or someone constructed them in advance. This is where the engineering problems begin. Constructing a wormhole, holding it open long enough for a ship to pass through, and ensuring that the geometry does not collapse during transit are all problems that make Alcubierre's negative energy requirement look manageable by comparison. Kip Thorne's own math explained why. Pull up Thorne's 1988 paper. The analysis starts from a simple question. What mathematical conditions must a space-time satisfy for a wormhole to be traversable by an ordinary spacecraft? Thorne listed the requirements, and the list is demanding. First, the wormhole must have no event horizon. An event horizon is a surface beyond which nothing can return, and if a wormhole had one, any ship entering would be trapped on the far side forever. This rules out most naturally occurring wormhole solutions, including the Einstein-Rosen bridge, which does have an interior horizon. A traversable wormhole requires a specific geometry where both mouths remain open and connected, with no one-way membranes anywhere along the throat. Second, the throat must be wide enough for a spacecraft to fit through. This seems obvious but has consequences. The minimum width depends on the tidal forces at the throat. In a narrow wormhole, the difference in gravitational pull between the nose and tail of a ship could be enormous, stretching the ship apart the way a black hole tidal force would. Thorne calculated that for a human-scale spacecraft to pass safely, the throat would need a minimum radius of several kilometers. Smaller wormholes might exist in principle, but no ship could survive crossing them. Third, the transit time must be reasonable. A wormhole with a short physical throat but an effective transit time of centuries due to extreme time dilation inside is not useful for practical travel. Thorne showed that throats with ordinary local geometry, where clocks tick at normal rates, are possible if the matter distribution holding the wormhole open is arranged correctly. Fourth, and most problematic, the wormhole must be held open against gravitational collapse. This is where the math breaks down to a single terrifying word: exotic. Ordinary matter curves space-time in ways that naturally cause wormhole throats to pinch shut. Gravity, as it appears in general relativity, is attractive. It pulls things together. A wormhole's throat, being a narrow region connecting two distant parts of space, wants to collapse under its own gravitational self-attraction the instant it forms. To keep the throat open, something has to push outward against that gravitational pressure, something that behaves like anti-gravity. Thorne's paper identified the substance that would be needed. It is the same substance Alcubierre's warp drive required: matter with negative energy density. Specifically, a kind of matter that violates what is called the average null energy condition, a mathematical criterion that ordinary matter always satisfies and that nothing known in nature violates. The amount needed is substantial. Thorne estimated that holding open a wormhole large enough to admit a kilometre-scale spacecraft would require a quantity of negative energy comparable to the mass of a large planet, arranged in a shell around the throat in a specific geometric pattern. The configuration is delicate. Small perturbations could cause the throat to collapse, and because the negative energy is stabilizing the structure, any fluctuation in the exotic matter distribution could tear the wormhole apart. Thorne was careful to note that his paper did not prove wormholes could be built. It proved that if the right exotic matter existed in sufficient quantity, the geometry would work. The question of whether that matter can exist in anything like the amounts needed remained open. It still is. There is also a timing issue Thorne identified that has become its own field of research. Wormholes, if they can connect 2 points in space, might also be able to connect 2 points in time. The same tunnel that shortens a spatial journey might shorten a temporal one, allowing signals or ships to arrive before they were sent. This possibility opens the door to closed, time-like curves, path through space-time that loop back on themselves with all the paradoxes that entails. The physics community has spent decades arguing about whether closed time-like curves are forbidden by deeper laws that general relativity alone cannot see. The debate has not been settled, but the exotic matter problem is simpler and worse. Run the comparison. Both warp drives and wormholes, in their original forms, require exotic matter with negative energy density. But the specifics of what each needs are different, and the wormhole version is significantly harder to produce. A warp drive needs negative energy distributed in a thin shell around a ship. The shell is moving inertially through space, and while its contents must be exotic, the requirement is essentially static. Once the shell is assembled and set in motion, it just needs to maintain its own configuration, not continuously resist gravitational collapse. Modern warp drive designs, as we've seen, have reduced or eliminated this requirement for subluminal cases. The shell can be ordinary matter. The warping comes from the shift vector geometry. A wormhole is different. The throat is a region of space-time under constant gravitational stress. The negative energy in the throat is not decorative. It is structural. It holds the wormhole open against the natural tendency of Einstein's equations to pinch it shut. Remove the exotic matter for even a fraction of a second, and the throat collapses, crushing any ship passing through. The wormhole is like a bridge held up by an active force rather than by its own rigidity. Cut the power and it falls. The quantity required is also larger. Thorne's estimate of roughly planet-scale negative energy applies to a wormhole wide enough for a kilometre-scale spacecraft. Scaling up to larger vehicles or longer wormholes connecting more distant regions increases the requirement proportionally. Some calculations suggest that a wormhole large enough for practical interstellar travel would require negative energy equivalent to several stars' worth of mass, all of it concentrated in the narrow throat region. There is also a distribution problem. A warp drive's negative energy can be spread across the bubble wall, with the density tuned to whatever the local geometry needs. A wormhole's negative energy must be concentrated in the throat, producing extreme energy densities in a small volume. If ordinary matter were packed that densely, the result would be a black hole. Exotic matter, by definition, behaves differently from ordinary matter, but the geometric demands are severe in either case. The stability picture is worse still. Researchers have analysed small perturbations to wormhole geometries and found that most configurations are unstable. A tiny disturbance in the exotic matter distribution can cause the throat to begin collapsing, and the collapse proceeds catastrophically once started. Making a wormhole stable requires precisely balanced conditions that may not be physically realisable. Compare this to subluminal warp drive, where the applied physics team has shown that positive energy alone can produce a working configuration. No wormhole analogue of that result exists. Every traversable wormhole solution anyone has written down requires some form of exotic matter in the throat. The no-go theorems in this area are stronger than the equivalent theorems for warp drive. While subluminal warp drives might be achievable with known physics, traversable wormholes appear to require new physics that nobody has found. There is one possible exception that comes up in speculative proposals. Quantum effects, particularly those associated with the Casimir force, can produce small amounts of negative energy in specific configurations. If those effects could be engineered at large scales, or if new quantum field theories allowed for stable bulk negative energy regions, wormholes might become feasible. The current state of physics does not support either possibility as realistic, but the future of physics might. For mission planners comparing options, the engineering trade is clear. Warp drive offers a path that, while still distant, connects to known physics and existing materials. Wormholes offer a path that requires a breakthrough in fundamental physics before any engineering can begin. Both are faster-than-light concepts. Only one has a visible roadmap. There is, however, one place in the known universe where negative energy has been directly measured. Switch to the laboratory bench. In 1948, a Dutch physicist named Hendrik Casimir was working at the Philips Research Laboratory in the Netherlands when he predicted a strange effect. Two parallel metal plates, placed very close together in a vacuum, should attract each other. Not because of gravity, which is far too weak to matter at such small scales. Not because of electromagnetism, since the plates are electrically neutral. The attraction, Casimir predicted, comes from the structure of the vacuum itself. Empty space is not truly empty in quantum field theory. It seethes with virtual particles, popping into existence and annihilating again on timescales too short to directly observe. These virtual particles correspond to every type of field that exists, including electromagnetic fields. At every point in space, electromagnetic waves of every possible frequency are briefly coming into being, propagating for a moment, and vanishing again. When two metal plates are placed near each other, they impose boundary conditions on these electromagnetic fluctuations. Certain wavelengths no longer fit between the plates because the wavelength is longer than the gap. Those wavelengths are excluded from the space between the plates but continue to exist in the space outside. The result is an imbalance. More virtual particles are pressing on the outside of the plates than on the inside. The imbalance produces a net force, pushing the plates toward each other. This is the Casimir effect. It is real. It was first measured experimentally in 1997 by Steve Lamoureux at Los Alamos National Laboratory, using metal plates separated by gaps of a few micrometers. Subsequent experiments have confirmed the effect to high precision. Modern precision instruments can measure it routinely. What matters for warp drive research is this. The region between the Casimir plates has, by all rigorous measures, a lower energy density than the vacuum outside the plates, lower than ordinary empty space, which is another way of saying the region has negative energy density relative to the vacuum baseline. It is the only confirmed example in physics of a place where bulk negative energy exists. The Casimir effect proves that negative energy is not forbidden by nature. The question is whether it can be scaled up to the quantities warp drives or wormholes would require. The answer, at least for current technology, is no. The amount of negative energy produced by a Casimir cavity is tiny. A pair of plates 1 square meter in area separated by a gap of 1 micrometer produces a total negative energy on the order of 10 to the negative 7 joules. That is less energy than a mosquito uses when it takes off. Warp drive designs, even the optimized versions, call for negative energy in quantities larger than the total electrical output of human civilization over centuries. The Casimir gap between lab-scale negative energy and warp-scale negative energy is 20 orders of magnitude. That is a factor of 100 quintillion. Nevertheless, the Casimir effect is cited in every warp drive paper that discusses exotic matter, because it proves the concept is not ruled out. Negative energy can exist. It exists in laboratories right now in tiny amounts, between precisely engineered metal surfaces. The question of whether larger quantities can be produced, stored and deployed is a question of engineering, not of fundamental physics. Several speculative proposals attempt to scale the effect up. One idea involves stacking many Casimir cavities together, each contributing a small amount of negative energy, with the total reaching useful levels. Another involves dynamic Casimir effects, where moving plates can extract additional energy from the vacuum. A third involves quantum fields other than the electromagnetic field, whose Casimir analogues might produce stronger effects. None of these ideas has produced a practical negative energy reservoir. But they are active research areas, and the engineering challenge, while immense, is no longer considered fundamentally impossible, which means warp drive on its longest timescale might not require entirely new physics after all. It might just require extraordinarily patient refinement of physics we already have. Run the scale calculation. A working warp drive needs negative energy on the order of the mass of a small spacecraft, converted to negative form. In energy units, that is roughly 10 to the 20th joules. A working Casimir cavity produces 10 to the negative 7th joules. To get from one to the other, you would need to multiply the Casimir output by a factor of 10 to the 27th. This is where the dream meets the spreadsheet. Engineers love scaling problems because they are usually solvable. Build more cavities, make them bigger, stack them, optimize the geometry, apply industrial manufacturing to what was previously a laboratory curiosity. Every technology in human history has followed some version of this path, from steam engines to semiconductors. Casimir scaling does not work like other scaling problems. The first issue is density. Casimir negative energy is spread thinly across the cavity volume. Packing more negative energy into a given region requires closer plate spacing, because the effect grows stronger as the gap shrinks. But there is a limit. Below a few nanometers, the plates start to interact via other forces, including van der Waals attractions and direct electron tunneling, which overwhelm the Casimir contribution. The densest negative energy Casimir cavities anyone has built produce density levels that are still hopelessly thin compared to what a warp drive shell would need. The second issue is stacking. In principle, multiple cavities can be arranged in a larger structure, each contributing its share of negative energy to the total. In practice, the cavities interfere with each other. Electromagnetic fluctuations outside one cavity are boundary conditions for the neighbouring cavity, and the net effect does not simply add up linearly. Stacking 10,000 cavities does not produce 10,000 times the negative energy. The gains diminish rapidly. The third issue is duration. Casimir cavities produce a static negative energy region, as long as the plates remain in place. But quantum inequalities, theorems proven by Ford and Roman in the 1990s, place strict limits on how long negative energy can persist in any given configuration. The more intense the negative energy, the shorter the duration it can be maintained. Pushing the density high enough for warp drive use would cause the negative energy to exist for only vanishingly small fractions of a second, not long enough for any ship to use. These constraints are not arbitrary. They emerge from the same quantum field theory that predicts the Casimir effect in the first place. Taking the theory seriously in one context means taking it seriously in all contexts. If the Casimir effect is real, the quantum inequalities are also real, and they limit how the effect can be exploited. Researchers have explored exotic workarounds. Dynamic Casimir effects, involving plates that oscillate at high frequencies, can extract additional negative energy from the vacuum, but the extraction rate is limited by similar inequalities. Squeezed quantum states, engineered configurations of light and matter that temporarily concentrate vacuum fluctuations, can produce brief spikes of negative energy, but the spikes are fleeting. None of the workarounds has demonstrated a path to macroscopic sustained negative energy regions. Some theorists argue that breakthrough physics might change this picture. A unified theory of quantum gravity, if it exists, might permit configurations that current quantum field theory cannot describe. New particles, if discovered, might have properties that allow stable bulk negative energy. A deeper understanding of dark energy, which already behaves somewhat like negative energy on cosmic scales, might reveal mechanisms for harnessing it locally. These are genuine possibilities. They are also pure speculation at present. No experimental evidence currently supports any of them. Warp drive via exotic matter scaling remains a mathematical possibility, with no engineering path. Which is why the applied physics team focused on designs that do not require exotic matter at all, and why the subluminal warp drive, for all its limitations, may end up being the version humanity actually builds, if we build one at all. But if warp drive is the cautious path, there is a particle physics concept that takes the opposite approach. A hypothetical particle that would already be moving faster than light if it existed. Load the particle physics primer. Einstein's speed limit says that massive objects cannot be accelerated from below light speed to above light speed. The energy required would be infinite. But what about particles that were already above light speed from the moment they came into existence, and never needed to cross the barrier. Such particles, if they exist, are called tachyons. The name comes from the Greek word for fast, tachys. They were first proposed in the 1960s by physicists including Gerald Feinberg as a theoretical possibility within the framework of special relativity. The equations of relativity, when applied to tachyons, produce some very strange behavior. For ordinary matter, adding energy increases velocity up to the light speed limit. For tachyons, the behavior is inverted. Adding energy decreases velocity, and removing energy increases it. A tachyon with minimum energy would travel at infinite speed. A tachyon approaching the speed of light from above would require infinite energy to slow down. The speed of light is a boundary they can approach from one side just as ordinary matter can approach it from the other. This sounds like a clever loophole. If tachyons exist, information might be transmitted at faster than light speeds without violating the formal structure of relativity. A tachyon signal sent from Earth could reach Alpha Centauri in days, or hours, or fractions of a second, depending on the tachyon's energy. The problem is that tachyons, as originally conceived, have not been observed. Every search for particles with the required properties has come up empty. The Large Hadron Collider and other high-energy facilities have looked for tachyon signatures in their data, and none have appeared. If tachyons exist, they interact with ordinary matter so weakly that our instruments cannot detect them, or they exist at energy scales our accelerators cannot reach. There is a deeper reason for skepticism. Quantum field theory, when applied rigorously to tachyon-like particles, suggests that they would produce instabilities in the vacuum itself. A universe containing tachyons that interact with normal matter would be unstable, prone to catastrophic transitions that would have occurred long ago and reshaped the entire cosmos. The fact that our universe is stable, and has been stable for about 14 billion years, is strong indirect evidence that tachyons of that type do not exist. Modern physics has mostly moved past classical tachyons. What remains is the recognition that some fields in the standard model of particle physics have tachyon-like properties during certain phases. The Higgs field, for example, behaves as a tachyonic field before it acquires its stable value, which is part of how the Higgs mechanism gives mass to other particles. But these are technical features of the mathematics, not faster-than-light particles you could use to send messages. Occasional experimental results have hinted at tachyonic behavior. The most famous was the Opera experiment in 2011, which briefly reported that neutrinos travelling from Kern to an underground detector in Italy had arrived 60 nanoseconds earlier than light would have taken to cover the same distance. If the result had held up, it would have been evidence of faster-than-light particles. The result did not hold up. A loose fibre optic cable in the timing system had introduced a spurious delay, and once the cable was fixed, the neutrinos arrived at exactly the speed of light, as expected. The tachyon concept has largely been abandoned as a serious candidate for faster-than-light technology, but the deeper principle it raised is still important. If faster-than-light signalling were possible, even in principle, it would create problems that go beyond propulsion. Problems that touch on causality itself, on the basic ordering of cause and effect that underlies all of physics. Because under relativity, faster-than-light signalling means something specific. It means the possibility of arriving before you left. Pull up the space-time diagram. Special relativity has a feature that most people never think about, because they never need to. Events that are separated in space but close in time can appear in different orders to different observers, depending on how those observers are moving. This is called the relativity of simultaneity. It is not a curiosity. It is built into the structure of space-time. Normally, This does not cause problems. Two events that are far apart in space and close in time cannot influence each other, because no signal can cross the distance between them in the available time. Whether one happened before the other is a question without a meaningful answer. Different observers assign different orderings, and all of them are valid, because the ordering does not matter for any cause and effect relationship. Faster-than-light signaling changes this. If a signal can travel faster than light, then two events connected by that signal have a definite cause and a definite effect, even though different observers might disagree about which came first. This creates a contradiction. Under certain reference frames, the effect happens before the cause. Let me make this concrete with a scenario. Imagine Earth sends a faster-than-light message to a colony on a distant star. The message arrives, and the colony responds with their own faster-than-light message back. In certain reference frames, specifically those moving at high speed relative to Earth, the return message can arrive at Earth before the original message was sent. The reply shows up before the question. This is not a theoretical puzzle. It is a direct consequence of Einstein's equations, provable by simple calculation for any faster-than-light signaling scheme. The conclusion is unavoidable. Faster-than-light communication between 2 points in space is logically equivalent to communication backward in time. Any technology that delivers the first delivers the second. The implications are severe. With backward-in-time communication, the standard paradoxes of time travel become live concerns. The most famous example is the grandfather paradox. You send a faster-than-light message backward in time telling your past self to prevent the very experiment that would later send the message. If your past self succeeds, the message is never sent, which means your past self never received the warning, which means the experiment did happen, which means the message was sent. The logic loops without resolution. Most physicists take the grandfather paradox seriously as an argument against faster-than-light signaling. The reasoning is that nature does not appear to permit logical contradictions. If faster-than-light signaling would produce contradictions, then nature probably does not permit faster-than-light signaling. This is called the chronology protection conjecture, proposed by Stephen Hawking, and while it has not been proven, it is widely believed. There are exotic scenarios where faster-than-light signaling might be possible without paradox. The many worlds interpretation of quantum mechanics suggests that each paradoxical signal simply branches a new universe, so the grandfather paradox produces parallel timelines rather than contradictions. Other theorists have proposed Novikov self-consistency principles, which argue that backward-in-time signals can only carry information that would not, in fact, change the past. Both proposals are speculative, and neither has been confirmed by any experiment. For warp drives specifically, the implications are serious. A superluminal warp bubble would, at least in principle, allow backward-in-time travel under certain conditions. Whether those conditions could be realized in practice, and whether the universe permits it at all, are open questions. The applied physics team and others working on warp drives sometimes note that their current, subluminal designs sidestep these paradoxes entirely because subluminal travel does not permit backward-in-time signaling. This is one of the quieter arguments for staying below the light barrier. Subluminal warp drives do not rewrite the laws of causality. They deliver engineering benefits without challenging the foundational logic of the universe. Superluminal warp drives, if they could be built, would force physicists to confront questions that nobody currently knows how to answer. There is one thing even theoretical superluminal drives cannot hide, though. If they exist, and if one of them fails, the failure leaves a signature. Open the detection paper. 2024. a team of physicists at Queen Mary University of London and collaborating institutions, led by Katie Clough, published a study titled What No One Has Seen Before: Gravitational Waveforms from Warp Drive Collapse. The paper does something the warp drive literature had not done before. It asks what happens when a warp bubble fails catastrophically and what signature the failure would leave behind. The setup is straightforward. A warp bubble, like any structured space-time configuration, is held together by a specific matter distribution. If that matter distribution becomes unstable, the bubble collapses. The collapse is not a gentle process. It is a rapid, violent reconfiguration of space-time itself, releasing enormous amounts of energy as the curved geometry relaxes back to flat. Clough's team used numerical relativity simulations, the same computational techniques used to model black hole mergers and neutron star collisions, to model what a collapsing warp bubble would actually do. They assumed a stiff equation of state for the matter inside, a reasonable physical choice, and watched the collapse unfold in the simulation. The result was a specific pattern of gravitational waves, the ripples in space-time that Einstein predicted a century ago and that LIGO first detected in 2015. A collapsing warp bubble, the simulation showed, would produce a gravitational wave signature distinct from any known astrophysical source. The signal starts as a brief burst, followed by an oscillating ring down at a characteristic frequency. The overall shape is different from the chirps produced by merging black holes or colliding neutron stars. This matters for a reason that might not be immediately obvious. If warp drives exist anywhere in the universe, and if they sometimes fail, their failure signatures would propagate outward as gravitational waves, potentially reaching Earth. A sufficiently sensitive detector could, in principle, pick up the signal. Not a warp drive in operation, but a warp drive that broke. The frequency of the predicted signal depends on the size of the warp bubble. Clough's team calculated that for kilometre-scale bubbles, the gravitational wave frequency would be roughly 300 kHz. This is much higher than the frequencies LIGO is designed to detect, which peak around a few hundred hertz. Current gravitational wave observatories would not hear a warp drive collapse, even if one happened in our galactic neighbourhood. But future detectors could. Proposed higher frequency gravitational wave observatories, using different detection principles than LIGO, are under development at several research institutions. If these detectors achieve their design sensitivity, they would open a new window on the high-frequency gravitational wave sky, and warp drive collapses would be a candidate signal they could search for. There is a speculative but interesting implication. The search for extraterrestrial intelligence, usually focused on radio signals or optical flashes, could be extended to gravitational wave signatures of advanced propulsion. An alien civilization operating warp drives in another galaxy would occasionally lose one. The resulting gravitational wave signals travelling outward at light speed would eventually reach Earth. By searching for these specific waveforms in the data from future detectors, astronomers could potentially detect not just the existence of alien civilizations, but their technological capabilities. This is a long shot. The probability that advanced civilizations exist, that they use warp drives, that their drives occasionally fail in detectable ways, and that we have instruments sensitive enough to catch the signal, combines to a small number. But it is not zero, and the possibility has given gravitational wave astronomers a new kind of signal to look for, independent of whether they ultimately find anything. The work also has a more immediate benefit. By modelling warp bubble collapse in numerical relativity, Clough's team developed techniques for simulating spacetimes that violate the energy conditions. These techniques have applications beyond warp drive in studying the stability of exotic objects throughout general relativity. The tools outlive the specific question they were built to answer, which means the hunt for faster-than-light travel, even if it never succeeds, produces scientific progress as a byproduct. Open the detector logs. The Laser Interferometer Gravitational Wave Observatory, LIGO, consists of two identical facilities in the United States, one in Livingston, Louisiana, and one in Hanford, Washington. Each facility contains an L-shaped vacuum tunnel with two arms measuring 2.5 miles in length. Laser beams travel down these arms, bounce off mirrors, and return to the intersection, where they're combined and analysed. When a gravitational wave passes through the Earth, it distorts the length of the arms by a fantastically small amount, on the order of 1/10,000th the diameter of a proton. The interferometer detects this distortion by measuring subtle changes in the combined laser beams. When LIGO went online in the 2015 detection run, it made the first direct observation of gravitational waves caused by two black holes merging more than 1 billion light-years away. Since then, LIGO and its international partners, Virgo in Italy and KEGRA in Japan, have detected dozens of gravitational wave events. Black hole mergers, neutron-star collisions, various combinations. The field of gravitational wave astronomy has become a mature science, with a rapidly growing catalogue of observed events and an ever-increasing understanding of the extreme astrophysics that produces them. None of the detected events has been a warp drive collapse. The reason is straightforward. LIGO is tuned for low frequencies, between roughly 10 and 1000 Hz. These are the frequencies produced by the kinds of astrophysical events LIGO was designed to find. Black hole mergers with masses comparable to stars, neutron-star collisions, supernovae. The detector is not sensitive to higher frequencies, and a warp drive collapse based on the Clough team simulations would produce a signal at 300 kHz. 3 orders of magnitude above LIGO's optimal sensitivity range. Building detectors that can observe higher frequency gravitational waves requires different technology. The arm lengths of kilohertz range detectors can be smaller, which is fortunate, but the sensitivity requirements are extreme. Proposals include superconducting resonators, levitated sensors, and microwave cavity arrays. Several groups are actively developing these technologies, though none has yet achieved the sensitivity needed to detect astrophysical high-frequency sources. The Applied Physics team, through its associated research division, has been arguing that these future detectors should include warp drive signatures in their search templates. The argument is simple. If warp drives can exist, and if they can fail, the signals they produce are specific and predictable. Searching for them is a reasonable addition to any high-frequency gravitational wave program, at minimal additional cost. Even null results would be informative, placing upper limits on the prevalence of warp-capable civilizations in our galactic neighborhood. The search for alien warp drives using gravitational wave detectors is a niche pursuit within a niche pursuit. Most gravitational wave astronomers are focused on the astrophysics their detectors are already tuned for, not on speculative signatures from hypothetical civilizations. But the field includes enough cross-disciplinary researchers that the idea has gained traction in certain circles. One concrete proposal came from a group including Luke Sellers of Applied Physics. The team calculated that a collapsing warp drive of a certain size and energy could be detectable out to a range of roughly 3 million light-years, assuming a next-generation high-frequency detector. 3 million light-years is a significant search volume. It covers the entire local group of galaxies, including the Milky Way, Andromeda, and dozens of dwarf galaxies. If advanced civilizations exist in that volume and operate warp drives with any regularity, their failures would be potentially observable. Whether any such civilizations exist, and whether any such failures have occurred in the time window we could detect, is unknown. The search has not yet begun in earnest because the detectors do not yet exist, but the framework is in place. When the detectors come online, the templates will be ready. There is a separate line of reasoning, independent of warp drive failures, that suggests other signatures might be detectable. Open the scanning strategy. In addition to detecting warp drive collapses, researchers have proposed searching for the gravitational wake of warp drives in normal operation. A warp bubble, by construction, creates a significant disturbance in space-time as it moves. That disturbance should radiate gravitational waves continuously during the bubble's transit, not just when it fails. The concept has been dubbed Ramacraft, a reference to Arthur C. Clarke's novel Rendezvous with Rama, in which a mysterious alien spacecraft passes through the solar system. The proposal is that if faster-than-light alien craft exist and are crossing interstellar space, they should leave gravitational trails that careful observation could detect. The calculation starts with the principle that any system involving the bulk acceleration of mass emits gravitational waves. A warp bubble, as established by the Bobrick-Martier framework, is effectively a shell of matter that has been set in motion. Moving masses emit gravitational radiation. The signature is different from a collapsing bubble, but it is still present, and it is still in principle detectable. The strength of the signal depends on the mass involved and the acceleration profile of the bubble's journey. For an alien spacecraft accelerating from rest to a significant fraction of light speed, or decelerating back to rest at its destination, the emitted gravitational waves could be substantial. The exact signal shape depends on the warp drive design, but a general prediction is possible. The wave would have a specific spectrum distinct from the chirps of merging compact objects, and the wave's direction would point back to the source. The detection range is encouraging. For a sufficiently massive craft, the signals could be detected out to intergalactic distances using next-generation observatories. Specifically, space-based interferometers like the Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, would have sensitivity to lower frequency gravitational waves than ground-based detectors. LISA's frequency range is well matched to the signals expected from large, slowly accelerating warp craft. This opens a new channel for the search for extraterrestrial intelligence. Traditional searches have focused on electromagnetic signals, radio transmissions, optical flashes, infrared excesses from Dyson spheres. All of these assume that alien civilizations use or leak electromagnetic signatures that we can detect. The gravitational wave approach makes a different assumption. It assumes that alien civilizations use advanced propulsion, and that propulsion leaves a space-time signature. The advantage of gravitational wave searches is that they are immune to the usual problems plaguing electromagnetic searches: dust clouds, intervening stars, frequency mismatches between transmitter and receiver. None of these affect gravitational waves. A gravitational signal from the other side of the galaxy arrives at Earth essentially unchanged, carrying information about its source. The disadvantage is that gravitational wave detectors, even the best ones, are fundamentally less sensitive than the best radio telescopes. A faint gravitational signal is much harder to pull out of the noise than a faint radio signal. The searches require long integration times and carefully designed templates to identify candidate signals. No detections have been reported. The search is still in its preparatory phase, with instrument development and template calculation both ongoing. The first serious searches for warp drive signatures in gravitational wave data are likely to begin in the late 2030s, once the next generation of detectors is online and operating at design sensitivity. Whether anything will be found is an open question. The universe might be full of warp-capable civilizations whose craft regularly cross interstellar space, or it might contain none. The observational program will eventually provide an answer, even if the answer is negative. A thorough search that finds nothing places meaningful limits on how common advanced propulsion is, constraining estimates of the prevalence of technological civilizations in our cosmic neighborhood. Meanwhile, on our own planet, the harder question is what humanity's own warp mission would actually look like. If the engineering challenges were solved and the physics cooperated, what would the program chart look like from here to there? Load the hypothetical mission timeline. Assume, for the sake of planning, that the physics cooperates. Subluminal warp drive is achievable within the century using ordinary matter, as the applied physics design suggests. Superluminal operation eventually becomes possible through some combination of refined metrics, engineered Casimir effects, or other breakthroughs that the current literature anticipates. What would the engineering stack look like? Laid out as a mission plan. The first requirement is energy. Even the most optimized warp drive designs call for energy budgets that exceed current global production by orders of magnitude. Powering a full-scale warp bubble requires fusion reactors operating at scales humanity has never approached, or matter-antimatter annihilation systems producing gigajoules per second sustainably, or some exotic energy source not yet invented. The Manhattan Project produced nuclear weapons in 4 years. A warp drive energy program would need to produce gigawatt-scale, long-duration power in configurations we barely know how to describe. This is not a decade-long effort. This is a century-long effort at minimum. The second requirement is matter engineering. The warp bubble depends on a precisely shaped shell of material with a specific density distribution. Building that shell and holding its shape against gravitational and thermal stresses requires material science that does not yet exist. Current high-strength materials can handle gigapascal pressures. Warp shells would need to handle stresses thousands of times higher. Work on metallic hydrogen, bulk nanotubes, engineered quantum materials and other exotic substances is ongoing but nowhere near the level required. The third requirement is instrumentation. Before any warp drive can be tested, instruments must be developed that can detect small amounts of space-time curvature at laboratory scales. LIGO measures gravitational waves at cosmic scales. Future instruments would need to measure static, small-scale curvature effects around benchtop apparatuses. Such instruments have been proposed, including refined Michelson interferometers and atomic interferometers, but sensitivity levels remain short of what a warp experiment would demand. The fourth requirement is theoretical closure. Current warp drive theory has gaps. The stability of proposed metrics under real-world perturbations is not fully established. The dynamics of bubble formation and dissipation are still being simulated. The interaction of a warp bubble with its surrounding environment, including interstellar matter and ambient radiation, is understood only in broad strokes. Each of these questions needs to be nailed down before any confident engineering design can proceed. Assuming all 4 requirements are eventually met, the first mission would probably be a short test flight. A warp bubble formed in Earth orbit moving a test payload to a nearby point and back. The payload would be uncrewed, instrumented to the teeth, designed to verify that the bubble behaves as predicted and that no unforeseen failure modes emerge. This test mission, by the most optimistic estimate, is at least a century away. By more realistic estimates, several centuries. If the test succeeds, the next step would be a longer flight. A warp mission to Mars, covering the 200 million mile distance in a few hours instead of 6 months. Then to the outer solar system, Jupiter in a day, Neptune in a week. Each milestone would validate the technology at a larger scale, building the engineering base for interstellar missions. The first interstellar warp mission would probably target Proxima Centauri. The distance, 4.25 light years, would be crossed in weeks or months depending on the drive's cruising speed. The mission would carry instruments to study the Proxima b exoplanet, which sits in the star's habitable zone. The return trip, if the ship returned at all, would follow the outbound path in reverse. This is not a mission plan for any living human. It is a sketch for the 23rd century, the 24th, the 25th. The specific timeline depends on factors we cannot currently predict, including breakthroughs in energy, materials, and physics itself. But the sketch is not fantasy. Each element corresponds to a known research program, to specific laboratories, to peer-reviewed papers. What the sketch does clarify is the shape of the problem. Warp drive is not a single invention. It is a technological stack, with layers ranging from fundamental physics to specific alloys. Each layer has to mature independently, and all of them have to integrate for the mission to work, which brings us, at last, to the honest verdict. Close the mission briefing, pull out the final report. The question at the start of this walkthrough was whether humanity has just found a real way to travel faster than light. The answer requires honesty about what the math says yes to, what it still says no to, and why the gap is closing even if the destination remains far away. What the math says yes to is significant. Warp drive, as a solution to Einstein's field equations, is valid. It has been valid since Miguel Alcubierre proved it in 1994. The subsequent 30 years of research have not invalidated the concept. They have refined it, optimized it, and narrowed the gap between pure mathematics and practical engineering. What the math also says yes to, with the applied physics work of the last 5 years, is that warp drive does not necessarily require exotic matter. Subluminal warp bubbles can be constructed from ordinary positive energy, using shaped matter shells and carefully chosen geometric parameters. This is a genuine result, published in mainstream peer-reviewed journals, and it moves warp drive from the realm of speculation to the realm of engineering in principle. What the math still says no to is faster-than-light warp travel without exotic matter. Every superluminal warp drive configuration identified so far violates at least one of the energy conditions. No-go theorems, while not absolute, are strong enough to make most theorists cautious about predicting a future breakthrough. The light barrier may hold for warp drives the way it holds for ordinary matter, just more subtly. What the math is ambiguous about is everything in between. Whether carefully engineered exotic matter, produced via Casimir effects or other quantum processes, can be scaled up to warp drive requirements. Whether new physics beyond the standard model might provide sources of negative energy we've not yet identified. Whether mathematical approaches not yet invented will open solution spaces the current framework cannot access. These questions are open. They may remain open for decades or centuries. The gap is closing in the sense that we understand the problem better than we did in 1994. The Alcubierre paper treated warp drive as a mathematical curiosity. The applied physics framework treats it as a classifiable engineering system. Warp Factory lets researchers evaluate designs systematically. Numerical relativity lets them simulate failure modes. Gravitational wave observatories might soon be able to hunt for warp signatures across the galaxy. Each of these developments is real, and each represents meaningful progress. The gap is not closing in the sense of being close to a working vehicle. The energy requirements, even for subluminal designs, remain beyond anything humanity can currently produce. The material science for building stable warp shells remains in the conceptual stage. The instrumentation for laboratory-scale tests does not yet exist at the required sensitivity. Every one of these obstacles is in principle solvable. None of them is close to being solved. For the mission planner, the honest brief is this: warp drive is real as a physics concept. It is plausible as a long-term engineering goal. It is not imminent as a technology. The interstellar voyages that fill science fiction, with starships crossing the galaxy in days and crews hopping between star systems as casually as passengers fly between cities, remain fantasy for the foreseeable future. But fantasy is not the same as impossibility. The difference between a fantasy and a long-term engineering goal is whether the physics permits it, and whether there is a visible path, however long, from current capability to eventual realization. Warp drive clears both bars. It clears them by a narrow margin. It clears them with caveats, but it clears them, and the research community continues to build on that foundation. Humanity may never leave the solar system, or we may, on some distant century, light up a warp drive and cross to Proxima Centauri in a week. The math says the second outcome is not forbidden. The engineering says it is not close. The honest verdict is patience. The honest strategy is to keep working on each layer of the stack, each refinement of the theory, each experiment that pushes the boundary one more micrometer outward. Because the distance to Proxima Centauri is 25 trillion miles, and a species that has walked on the Moon, landed probes on Mars and detected gravitational waves from black hole mergers billions of light years away does not give up on a problem just because the numbers look hard. The mission brief ends here. The voyage is still being planned. The engines, one equation at a time, are slowly learning how to work.